Here we are looking at how to combine surfaces into a solid polysurface, which means that the geometry created the polysurface, or closed BREP as Grasshopper calls it, is more or less ready for production, depending on what tool you will use. 3D printing or CNC machines or the like. Here we have constructed a car wheel, let's call it that, and which is then also parametrically adjustable, like an example. Whoops, I'll get it like this, for example. You see that there is an opening, 5 openings in this, which is diverging downwards in this manner. You can set that if you want to, and you can also go and edit the original geometry. So every time you move that, it will affect the whole system here. So you can have whatever curve you want to, really. What I also wanted to show is that how to create a surface which is good and what is bad. So in this case, if I bake this, we are going to look at it also with a Zebra viewer, which you can find here in Rhino, Analyze Surface and Zebra, which gives it stripes like this, which means that you can see if there's any discrepancies in the surface, like edges that don't go over in smoothly according to the mesh. Sometimes there are actually visual discrepancies also in the Zebra. Here you see there, well, that's more of a pixel situation, but you see that they are all smooth if you go around like this. And we're going to look at an example also where it's not like this. So let's model this then from scratch, and I will take you through a couple of stages and show different settings and so forth. As you can see, I have already drawn a shape. I plan this to be 5 rotations in the car wheel, so you can draw whatever shape you want to, of course. Just be a little bit sure with the dimensions. You can also work completely dimension free, of course, but now I have set this to actually correspond to car wheel. So if I measure this, I'm working with, this is on a little bit more than 450 millimeters, for example. So then I know that is because I know that a car wheel is approximately 480 millimeters. So let's do a circle around this. If I double click and type circle, and you see that on default, you know that the circle is landing in Origo in 0.0.0 and has a radius of 1. So I can take out a slider here, and let's set that to 1000. And we're working in millimeters, so I can actually go to integers here, so we don't need any floating points on that in that tolerance. So let's say I go to 480. So you see I did this already, so I know it's going to fit. And we have to, of course, pick this curve in. So we take a curve from up here, from the parameters, right click on it, set one curve, and you take this one. Remember that this curve must be joined. So if you have several curves, you should mark them and join them in Rhino with this icon here to the left. Note also that I made edges here, like sharp edges, and that is because I want to show something about the surface construction. So if you do that too, that would be more would fit more to what I'm going to show, but of course you don't have to. So then you can just be aware of what happens here. So I'm going to rotate that around, and I think you might already know that that's a component called Polar Array, which you also find here on Transform and on the second array section there. So I can take that in, and it of course becomes quite many, because on default the number is set to 10. So what one can do is actually, if you want to change this later on, you can do slider, and you can do integer by pressing N and take maximum 10, for example. And why did I take maximum 10? Since I want 5. I mean, if I have 5, it looks pretty perfect, right? But the thing is, maybe you want to have 8, and then you can later on scale with 1D scale here. You can scale it until you actually find some other design like this, for example. But now I'm going to go with 5. And of course one has to design this shape a little bit so it fits, but that's a completely different story. So now I have these. If one is really happy with the shape, by the way, that you've made, you can always internalize data, then it becomes part of Grasshopper, and you don't actually have any geometry in Rhinoceros anymore. Nevertheless, now we have two sets of curves. In one of the components there's one curve, the circle, and in the other component there are 5 curves that we have made. So we should now actually build a planar surface from this. So we go to surface, and we choose this boundary surface, which you also can find in Rhino here, but then it's called surface from planar curves. It's actually more or less the same function. So you add this by holding shift, and what happens now? Well, it's actually building 6 surfaces because we told it to do that. But if we do, it's because it's different lists, right? Again, so there's one list with this 5 and one list with this surface circle here. But if we flatten, then it will become one list, and then Grasshopper would automatically make the holes. So there you have the shape that we're talking about, that we're after. And then we can look at this like we're building floors and walls. So here is a floor, and then we're gonna build walls, and we're gonna have another floor later, lower. So what we can start with is simply to move both the circle and the array polar at a specific amount downwards or upwards if you want to. So we can go to the move component, double click, type move. Also you find that here on transform. So let's try to keep all of these in a good structure. So I'm gonna move this one, so that's gonna be the bottom one, right? So depending on how you choose to set your Grasshopper, I would do this because I move it downwards, then I know where it is. So it's like a vertical setting here is corresponding to the vertical setting, vertical appearance here. The vertical movement, I mean. So we can have minus, I'm going downwards, attach that, they're all orange because there's no info. And I happen to know that a car wheel is approximately half the size of the radius, so 240, like that, and then it moved down. So now you wonder why I didn't move this, right? But it's because we're gonna scale these a little bit, the holes, so that we got another appearance, which is not. Otherwise, we could have just extruded this downwards. So this is, I want to show how to combine surfaces, and then I can, if I extrude, then it's already a solid geometry. This is more complex, has much more facets to it. So we have to move these as well. We can simply copy that one, and we have the same movement factor to it. So now I have another floor, but I wanted to diminish these, right? So one thing one can do, depending on the shape you have, you can also scale them. So if you go to scale, look at that first. We need the geometry to be scaled. We need a center of scaling and factor, which is 0.5 on default. Just see what happens here. If we enter all of them, of course, it's gonna take all of them. But if we instead measure the area of each and every one of these, then they will have also a center point. So if I double click and type area, attach that, and here is the center point coming out. So if I take that in, then we have something here. But now we see something strange. If I were to build surfaces, walls in between here, what would happen? This surface would be very strange, wouldn't it? You see, it would like almost cut into itself. I mean, if that's not really, maybe that's a design idea, then it's one thing. But in this case, I would not like to have it like this. Or then one has to consider a different solution. So one very good solution in this case is to offset that curve. So offset. If you search for that, offset curve, then you can hover the inputs curve, of course, and then the distance, the plane we're working on, it's still the XY plane, it's just moved, it's just a bit downwards, it's going to offset on X and Y. And then we have different settings for corners of the curve, which is not really relevant right now. So if we take that one, I'm just gonna look if that was the correct one. Yes, it was. So on default there is a setting that's actually 1. Then that's pretty good actually, because then you can zoom in and see what direction it is. If it's a positive number, it's going usually inwards, but this is depending on how you drew the curve. So it's going inwards now, so I can use a positive number here. If this green line were to be outside, then I will have to use a negative number. Yeah, so I can take, for example, this is a very high number, of course, so this is going to look strange. I strongly recommend to diminish that into like top value, maybe 50. I have to design my way through this, so I actually am sure of this. Maybe it was a little bit too little actually. I will go for 100, which I won't use, by the way, but it's just to have the upper level. So that's a different situation, right? You have already see that you're gonna be able to build some nice surfaces there. Yeah, so we have now, let's sum up what we have. We have already made a surface here. We have moved and scaled or offsetted these curves. This one is just simply a copy, so that one we can hide. So it looks like this. And in the bottom we also have a circle. So now we have everything we need to build this actually. So let's build some surfaces again. These ones and these ones is the same as the boundary surface, right? So we can copy that and add these instead, also flattened, of course. Then we have a lower floor and a top floor, so to say. And then we need something in between these, between these curves and the offsetted curves. And one good one to choose is ruled surface, which I usually, or you can also do it with a loft, but in this case we are sure loft looks like this. Double click. Then we have just one input for all the curves. In this case it's much more secure, since we have two sets of curves and we have one input per curve bundle. So this one goes in there first and this one afterwards. And now it looks a little bit awkward, doesn't it? That is because why? Then we have to analyze this a little bit, because we see also that the cables are different. That's an indication of difference in lists. So we can look at the lists just to understand the graphed and flattened that we're going to have to do. We have to transform the list somehow. So I hope you can see this well now. So we have this one going in the A, and this is the list coming out of it. And then we have this one as well. So I copy this and look at it instead. And then you see a big difference here. In the first one, we have 5 closed planar curves, 5 lists. One list with 5 closed planar curves in it. And in the second component, we have 5 lists, each containing a planar curve. So this means that we have to change one of them to appear like this. One thing you can do if you're unsure is to simply type graph in a search for it. You can select a component called graph tree and attach it to the list. Copy again here and look at the transformed list. And this looks exactly like this one. That would then work. That means you can graft this input. The other way around, if you flatten tree, looks as a symbol, looks like a chopped off tree there. You can look at this list and you copy the viewer and look at the list. So then you see that you can also actually make this work by flattening the B if you want to. So you can do either way. I hope you can follow that one. It's graph and flatten is list modifications, which are very essential when you're working with Grasshopper. So if I graphed this A input, we have the result we want to have. If I then flatten the B input, we also have the result we want to have, but probably maybe some discrepancies. You already see something going on that we have to look at much more closer in order to make this correct. So I'll see again if that happens also with the graph. Yes, it does. So something's going on. So let's now combine all these surfaces to make a closed polysurface. And something that easily forgotten now, we don't have a wall on the outside, so we need 2 walls, 2 sets of walls. First we have, first set contains these 5 walls, and one other set contains only 1 wall, the outside one here. And that is actually the circles, right? So if we keep it, the structure like this top floor, bottom floor, walls, and another set of walls. Now I copied that. I usually disable if I copy something, because if you copy and then attach something like the circle to this offsetted curves, it could become a little bit too much to calculate, and that's an error more or less. So let's attach the circles to another instead, and we don't need a graph in that case. You see already the cables, it's the same kind of list. The list that changed here is because it has the information about the offset. That's why the list was changed. So we can take out the graph and enable this one, and then we have a very nice wall on the outside. To join these then, we will double click and search for brep join, which is this one. Also to be found on surface and utilities on the right side there. So if you open utilities, you see brep join here. Then you can join a lot of surfaces into one closed polysurface. Holding shift, putting them together, creates then something like this. And then you also see something with the cables, right? Different kinds of lists going into one component, which makes 6 different entities in here. It's actually not joined. So in this case you have to flatten the whole list so that it understands that it should combine each and every surface that goes in. Then if you hover, you see it says closed brep instead of what it says previously. So now we are all more or less finished with this one. We just have to look at the surface quality. So let's bake it and take it out here. And if we can double click on the Grasshopper here so that it gets diminished. Sometimes you must watch out with diminishing here, and because that sometimes that doesn't work on all computers. So if you select that one, sorry, this is in the way now. So analyze surface zebra, like that, and we take a look at the structures built here. They look pretty fine, don't they? Or is something strange? Here, for example, something very weird is happening. So this is, if you would send this to someone else to work further on it, there will be some complaints, I would say, because now it could be something strange done with the communications between programs or to the manufacturing. If this, you see, it's not fluently going over into the other surface. This happens actually on that part everywhere here. This means we have to do something about the surfaces, and this is actually because we have this sharp edge. The ruled surface command can't really handle that, and wonders how it's going to build the surface. A good solution for that is to, instead of combining I mean, you remember that the surface is a closed one. That's what we said from the beginning. I mean, usually it doesn't happen all the time. You might have drawn it otherwise as well. But in this case, I'm just showing how you can make surfaces better so that it actually looks good in the zebra or any other analyze method. So what we can do instead, we can actually explode these and then make another ruled surface. So remember which ruled surface we're working on here. Sometimes I actually just make like that. I mark it and I press Control G to group it, and I have a purple background that I can also mark and delete if I want to afterwards. But now, so that you just don't, so you remember where it is. So we have the offsetted and the array polar. These are the ones we're gonna have to deal with. So if you double click and type explode, it will automatically divide these into curves, and it uses, of course, the edges on default to divide the curves. So now we have how many curves? We have 10 instead. I have 5 from the beginning, closed ones. Now I have 10 open ones. So we should use these to build a ruled surface instead. So before I enter everything into it, I usually disable again like this, so we can work freely. So I will put that in here, and I would take out the graph. But what will happen with this one? I can enable it fast to just show what happens. And it's not really at all what we want to have, you know, because this one is a closed curve, 5 closed curves, and here we have 10 open ones. This needs to be it as well. So I disable there. So what would happen if I would this is something that could go wrong if you would move these downwards and put them in here. Then you would think maybe it will work. It would look like this. So I will test things before I do something. So if I move open curves and offset them, they're going to overlap like this. This is not going to work at all. So we have to go back like that. And we have to explode this one and then put it in. Then we have the same kind of curves coming out. Again, we can actually look at the lists coming out. They're supposed to be, I mean, already by hovering we can see what kind of list it is. It's obviously then 10 different lists, right? And this is also, I'm just showing this to actually understand this lists thinking in different kinds of lists. So here we have 5 lists with each 2 curves. So do you know why? Well, it's because we have it's the same in the other one. So we exploded one list, this one, closed planar curve, and so forth. And when we also explode this one, 5 different values, it turns into both of them turn into well, they keep the first setting, the first curve you had, and creates a new list for that curve containing the exploded parts. So 2 per list. And this is of course great, because then it means they are, so to say, we could call it that they are grouped all along the algorithm. Anyway, I will then put in the explode curves here and press enable to see what it looks like, and it indeed works quite well. Already now the discrepancies in the edges are gone. They're not there anymore. So now we can bake this one. And we take it out here somewhere and we look at it in the Zebra viewer again. Remember that the Zebra, I mean, if you go here and you take Zebra and select objects of Zebra stripe analysis, and then we select this closed polysurface. And now we look at the edges. Don't beware that there's actually a pixel situation going on here as well. That's a bit strange, but still, this was the point where it was bad before, and now it's good. Now the surface is correct. So we always have to look at it with we have to analyze all the surfaces we build to see if they are correct. You can also look at it in a different view here, like, or in a rendered mode, like this. And we can also, to be absolutely sure, go to this select function here in Rhino and click the little arrow. Then a lot of selection tools come out. For example, this one is very handy to use. If you're gonna 3D print this, for example, we click the little arrow and we ask Rhino to select all closed polysurfaces. So now it's a little bit exciting to see if it's, yes, it is. It is a closed polysurface. It means it has no holes. It has then mathematically a thickness. It's a solid object ready for production or export. Well, to export things, you always can go here to export selected, for example. Then you select what you want to export, and you have a lot of different file formats right here, from IGES to OBJ to STL and so forth. So that was a little bit of an overview of how to combine surfaces and to analyze the result.